This isn't new anymore, so I'm just going to jet through it really, really quick, okay? Let's just get the general idea, and then we'll go straight to the formulas, okay? General solution. Yeah, general, right. The whole idea is that usually if you want specific solutions for trig functions, because they go on forever, you'd have to list them all off, right? So the usual limitation you get, like from, say, year 10, is that we give you a domain, say 0 to 2 pi, and then say, well, just give us some solutions in there, okay? But you guys know better than that. You know that they follow a pattern. So general solution is about taking advantage of that pattern, yeah? Okay, so I'll start off with tan. If you remember, that was the easiest one because, put it over here. Because if you have something like, say, solve tan x equals 1, okay? So let's put in 1. Actually, it should be about, let me think, approximately here, I'm guessing. If you were to plot y equals 1 in there, right, the solution to tan x equals 1 will be all of the points of intersection, right? And so you can see them there. So the first one is 45 degrees, pi on 4 radians. And then when you want to look at the subsequent ones, right, because the shape of tan is so simple, it doesn't go up and down, it's just the same thing over and over again, how do I get the next solutions? From pi on 4, I do what? I just add pi, right, because that's the period. So you got pi on 4, and then if I add pi, I've got 5 pi on 4. Oh, that's a terrible, well anyway, you get the other one. And then to get the next one, you're going to have 9 pi on 4 and so on. Okay, so we said the general solution for tan x is equal to, and then we had a number here, any number, so our number here was 1. But if we call it, say, c, okay, we said that x is equal to, well, you start with the base angle, right, whatever angle you work out, and that angle pi on 4, right, it comes from this angle here. So you can say either alpha, right, where that's your base angle, or theta or whatever, or you could say, because we know our inverse trig functions now, right, you could say tan inverse of 1. That would do it. So I could say tan inverse of c, okay, plus, and then you've got subsequent periods, right, so m pi, where n just has to be a whole number. Okay, so is this ringing a bell? Yes? So, there's tan. When we do cosine, what was the difference? Okay, so instead of, say, tan x equals 1, let's pick something like cos x equals a half. So, okay, so what kind of solutions are we getting? What's the first one for cos x equals a half? Radians, radians. Pi. Good, yes, pi 3. Okay, so you can see the first approach you can take is you can go from there, and just like we did before with tan, right, you can go forward a whole bunch of the period, okay, just one lot. So that would be forward 2 pi, so that would land you on this solution here, right, which is adding 6 pi on 3, so that'd be 7 pi on 3, right? And you can do that again if you'd like, but you can see we've missed a solution, right? Not only can I go forward 2 pi, but I've also got, if you put in 2 pi there, you've also got this solution here which I missed, right? So from each lot of the period, 0, 2 pi, and 4 pi, and so on, okay, you go forward the base angle, and then you go backwards the base angle, right? So I guess this one here would be 5 pi on 3. Okay? So therefore we said, if you've got if you've got cos x is equal to c, right, then the general solution for cosine is, you start from your lots of 2 pi, right? So you've got 2n pi, or 2m pi, it doesn't matter, right? And then because you want to go forward and backward, right, I've got my plus or minus, okay? And then you've got your base angle here, which I guess we could say is cos inverse of c. Okay. Lastly, sine. Okay, so let's do sine x equals a half again. Actually, so that'll give us a nice easy angle. Sine x equals a half. So the first solution is pi on... Come on, guys. Sine x equals a half. Easy one. Pi on 6. Thank you. Pi on 6. Okay? So again, we can take the same strategy. We can go forward 2 pi, and that'll land us on one of the solutions, right? But we've missed one, again. Okay? We've missed this one over here. Okay? So I can't just go 2 pi, even though that would give me some of the solutions. Only give me half of them. So how do I get the other half? Well, we noticed. Now here, if I go at intervals of pi instead of 2 pi here, right? So if I think about 0, and then pi, and then this is 2 pi, and then, let's see here, what have I got? This would be 3 pi on 2, this is 4 pi. What I need to do is take my base angle, okay? And for even lots of pi, like 0 pi and 2 pi and 4 pi, for even lots I go forward, the base angle. So that's why from 0 I go forward, from 2 pi I go forward. If I wanted to keep going for 4 pi, I would go forward. And then for odd lots of pi, I have to go backwards. Same base angle, right? But you go backwards here to get 5 pi on 6. You go backwards here to get, I don't know what you get, but you get the idea, right? Odd lots of pi, I'm going backwards. So therefore, when you've got sine x is equal to a constant, okay, we said that, well, it goes off every single lot of pi, not just the even ones, okay? So we started with n pi, okay? But then, to take into account the fact that sometimes you go forwards and sometimes you go backwards, what did we add next? Yeah, we added this switching thing, right? So that was minus 1 to the power of n. Okay, and the reason why this is useful is because when n is even, this will become positive, so it takes you forward. And when n is odd, this will become minus 1, so it takes you backward. So that's really kind of cool, actually. So forward or backward, the base angle, which is this, sine inverse of c. Okay?